notes for section 4.4 on similarity and diagonalization. So we say that A is similar to B. Here's my definition. I'll just kind of display it again. The guys that took the quiz definitely knew this already. So we're going to say that A is similar to B if that's math notation for there exists. If there exists an invertible n by n matrix P such that, here's the equation you need. P inverse AP is equal to B. And if you have that, we're going to say A and B are similar, and we even do what we do in geometry. We do this. Okay. And I guess the other fact I want to show people is that, no, I guess this was our work from yesterday. Let me go a fresh page for today. So 4.4, similarity and diagonalization. So if you have, you know, this equation is true, let's say, let's suppose we know that, again, it was P inverse AP is equal to B. I guess what I pointed out already to Tyler is that if you multiply on the left by P, and then if you multiply on the right by P inverse, then you get A is equal to P, B, P inverse. So you can put these things back and forth. Or, let me just do one of them. Here, let me take that red equation and multiply on the right by P. Then you get this equation, right? You can write AP is equal to what?
PB.
Peanut butter, PB, right? Sometimes this is the best way to show that things are similar, because finding an inverse of a matrix takes a lot of work. And so maybe you're better off just multiply A times P, multiply P times B, and see if they're the same. Then you'll know A and B are similar. Now, if you have, so this is an important theorem from the reading, okay? Theorem, I guess it was 422, okay? If A is similar to B, then I'm just going to say lots of nice things are true. Like what?
B is similar to A.
Okay, that's one thing.
I can't remember off the top of my head anything.
So it turns out that they have the same rank,
characteristic polynomial.
Yes, and determinant, and if they have the same characteristic polynomial, they have the same eigenvalues. Yeah, maybe the most important one, I think, is that the characteristic polynomials are the same, but they have the same determinant. There's a lot of nice things. If one's invertible, if and only if the other one's invertible, right? Now, here's a question. If you had two matrices with the same characteristic polynomial, does that mean that they're similar? And that answer is no. This is a one-way implication, okay? It's hard to show that two matrices are similar, but if you know they're similar, you get a lot of nice things from it. How do you show that matrices are similar? Maybe this is one way. If you can come up with a matrix P such that this is true, then you know that they're similar. Okay?
Question about P.
Yes.
So, can it be any matrix? I know that said they're not unique to the...
They're not unique. It could be any...
As long as it's square and invertible?
Yes. There can be many, many different P's that work for similar matrices. Right. So here's the theorem, right? A is diagonalizable if and only if it has n linearly independent eigenvectors. And I'm not going to do the whole proof, but I am going to make the point that if it didn't, the way we formulate matrix P when we diagonalize is we use eigenvectors. In particular, you want to use a basis for each of the eigenspaces, right? So you're going to use these vectors, and I'll show this more clearly in a minute. But the fact that your matrix of eigenvectors is linearly independent is why it has an inverse. Otherwise, this wouldn't even be possible. And I think that's enough said about that. But I think what's more important is to understand, for it to be diagonalizable, let's have an example of one that is and one that isn't, all right? And I really like the examples in the book. Here's example 4.25. It's the same as 4.18 from the previous section, the same matrix. And in that section, we figured out the basis for the eigenspaces. Now, what do we know about this? This one, the characteristic polynomial of matrix A, do you know what it was? Well, we know what the eigenvalues are, right? So,
wouldn't it just be lambda minus 1 times lambda minus 1 times lambda minus 2?
that's right. So the characteristic polynomial of that matrix A, I would write it as lambda minus 1 squared times lambda minus 2. And so what that tells me, for example, the algebraic multiplicity, this is something I've been making a big deal about, right?
Oh, it has to be 1 for all values, otherwise it's not.
So here's the deal, right? This algebraic multiplicity is 2, and this algebraic multiplicity is 1. Right? But what's true about this exercise is that the geometric multiplicity is what?
1.
1. How come? Because the basis, all the eigenvectors that are fixed vectors or have an eigenvalue of 1, they all look like that, 1, 1, 1. So if you take this matrix and multiply by 3, 3, 3, you get 3, 3, 3. The geometric multiplicity is only 1, and that's kind of the key difference between 4.25 and then example 4.26. In 4.26, let's look at it.
Does that mean that the algebraic, the sum of the algebraic multiplicities and the sum of the geometric multiplicities have to be equal then?
Well,
Because then there'll be enough.
if they're equal, if they're the same is what I should say. If each of the algebraic multiplicities is the same as each of the geometric multiplicities, then your matrix is diagonalizable. But this one, notice the one we were just doing, here's the punchline. It's not diagonalizable. So then they do 4.26, and they show this situation, and we already did it in 4.19. We calculated a basis for each. It had a double eigenvalue of 0 and another eigenvalue of -2. So I guess, for example, 4.26, right? The polynomial would be what? It would be lambda squared times lambda plus 2, right? But in this situation, not only do we have algebraic and geometric multiplicity is 2. So the algebraic and geometric multiplicity for this one is 2, and then for this one it's 1. You don't really have to check the ones that are multiplicity 1, right? The only thing you have to check is, do we have the same algebraic and geometric multiplicity? If we do, that's diagonalizable. Okay? Does that make sense?
Yep.
Cool.
So then another thing you could say is that plus the other one would have to equal n, you could say.
All the multiplicities, all the algebraic multiplicities add together always equal n, yes. And if it's diagonalizable, then the same will be true for the geometric multiplicities. So now actually now you can prove this theorem. that you mentioned to me earlier. Why is this true? Well, if it has n distinct eigenvalues, think about what the characteristic polynomial looks like. Each algebraic multiplicity would be 1, because they're distinct. And therefore the geometric multiplicity is also 1, and so it's diagonalizable. Kind of follows from the theorem that we were just talking about. Then they have this nice diagonalization theorem, which I could spend time on. But I think what I want to do instead, well, I guess we've been proving these are equivalent. A is diagonalizable. The algebraic multiplicity of each is equal to the geometric multiplicity. And then you could talk about the union of the bases of the eigenspaces containing n vectors. It's all the same.
What does that mean?
Well, union means put them all together. Basis, they mean, for example, here, back to this exercise. How many eigenvectors would be in all the bases? Well, there's 2 in this one and 1 in that one, so there would be 3. Diagonalizable. What about the union of all the ones for this one? There's only 2. That's not n. N is 3. Not diagonalizable. It's just another way of saying the same thing. Union is nice math language, you might say. Intersection is another nice math word. We're talking about sets. So I thought maybe it'd be smart to show you guys way back when we first started talking about eigenvalues, I gave this discovery packet, which is really hard. And I didn't expect, I think I had you guys skip this one, number 3, or maybe you looked at it a little bit, I don't know. But I thought it might be nice to revisit it now. Okay? So what I did while people were taking the quiz, or a person was taking the quiz, is we inputted F and these vectors V1 and V2 and V3 into MATLAB. And the first problem says, show that these are all fixed vectors. So let me show you that they are fixed vectors. Here's V3, right? And here's F times V3. Ta-da. Same thing back. So it's a fixed vector. That means a V3 equals 1 V3, so 1 is an eigenvalue, right? And actually, if you look at it, this is an eigenvector, that's an eigenvector, and that's an eigenvector, right? And so maybe what's interesting would be to do this. We say, okay, let's find the characteristic polynomial of F. Well, there it is. I'm going to write that down. Okay? So, how do you write that down? What would it be? Lambda to the 4th.
Or, yeah, sorry, lambda. Minus 8 lambda to the 3rd plus 18 lambda squared minus 16 lambda plus 5.
Yeah, let's write that down. That is, let me zoom out so you can see, that's the characteristic polynomial of F. So I'll say poly of F is equal to that. Right? And so, one question is how do you factor this thing? Well, there's an old trick from college algebra. Were you in my college algebra class? No.
I just skipped it.
Oh, yeah. But I'm sure you at some point, because we even do this in calculus sometimes, you learn about synthetic division. So if 1 is an eigenvalue, then what I can do is I can just, again, write down these. What I'm really doing is I'm taking that polynomial and I'm dividing by lambda minus 1. And so, you remember this trick? Have you seen this before?
We've done a lot of synthetic division.
So it's just add and multiply. But yeah, you basically have just shown that this is equal to lambda minus 1 times whatever you have left. I guess it's lambda cubed minus 7 lambda squared plus 11 lambda minus 3, right? Well, you can actually keep going because, see, lambda equals 1 can be taken out again. So I could divide this by 1, and I think it comes out even. Let me just double check that. Yeah, I get another remainder of 0. And so another way to write this is lambda minus 1 squared times what? It would be lambda squared minus 6 lambda plus 5, right? Which factors into what?
X, or lambda minus, or plus 6, lambda minus 1.
Nope. You got it kind of backwards. You got to look at the 5, not the 6.
Oh, 2 and 3. Plus, minus 3 minus 2. Right?
No, because that won't give you 5. Here, well, one way to do it is we could do this again. We can take out another 1. And what you learn is that it's lambda minus 1 times lambda minus 5. This is my favorite factoring problem to give beginning algebra students because of the messing up between the 2 and the 3 and the 1 and the 6. They both kind of do something to get you 5. Anyways, what did we just learn? We learned that this is really lambda minus 1 cubed times lambda minus 5. Okay, so what does that mean? It means there's 2 eigenvalues. What are they? 1 and 5. What about multiplicity?
Algebraic multiplicity of 1 would be 3.
That's right. What about geometric multiplicity? Well, it turns out that basically what we showed in part A is that the geometric multiplicity of 1 is also 3 because there are 3 linearly independent eigenvectors that you can use for that eigenvalue. In other words, this is a basis, a 3-dimensional basis of that eigenspace. If I went through the calculation where we say find a basis for the eigenspace associated to 1, that's a long calculation. What we would get are, or what we could use, are the vectors in part A. We might not get those. We might get multiples of those, right? But what you could use as a basis would be the vectors in part A. That make sense?
Yep.
And it means that F is diagonalizable. Because this V4 here, right, 1, 1, 1, 1, let me throw that in MATLAB also. So V4 is equal to 1, 1, 1, 1, and then if I transpose it, then I won't have to write the column with all the semicolons. So that's the fast way to do it, right? And so now I can do V4, and I can do F times V4, and I can see that, yes, 5 is also an eigenvalue. So does it correspond to a fixed direction? Remember, back then we didn't have any of this language. We were just like, what are these things? And I was trying to show you they're fixed directions. A times this V4 is the same as 5 times that V4. That was the point. Okay, part C. Let S be the 4x4 matrix whose columns are V1, V2, V3, and V4. Verify that the columns of S are independent. Let's do that. How do we do it? Well, in MATLAB, what I would do is I would say S is going to be the matrix where you take V1 and put it next to V2 and put it next to V3. These are all column matrices, so this should work. There it is. That's S. How do we verify that the columns are linearly independent?
Reduce row echelon.
So that's one way, is you could reduce row echelon form S and see what it looks like. That's good. Actually, you could probably see that you would have gotten that by hand. I mean, just think about adding the first row to the second row. And then adding the second. I mean, eventually you get there. Okay. Another thing you might have tried is this, right? It's not 0. That's good. But notice it's not 1 either. When you do reducer echelon form, we know you do change the determinant. That's part of the last section's homework. Okay, question D from the guided study. Relate the columns of F times S to the columns of S. All right, well, let's check those out again. Here's S, and here's F times S. Although maybe you can guess what this is going to be. Does that make sense to you guys? What's the only thing that changed? Because column 4 is an eigenvector with an eigenvalue of 5. The other ones are eigenvectors with eigenvalues of 1. So when you multiply by F a whole matrix, you can do it column by column, right? Okay, question E. This would have been very hard before today, but maybe today we can get it. Find a matrix M such that F times S is the same as S times M. Maybe it's not that hard, but it's much more clear about what it actually means today than it was back then. I don't know. Let's look at our calculation. Can you guys come up with, what are we trying to do? We want F times S to be the same as S times M. There's S. What would I want M to be?
The identity with 5 in the bottom right?
Exactly. I'm going to write it this way. The diagonal matrix where the diagonal is 1, 1, 1, 5. Nice job, Tyler. That's awesome. There's M, right? And so, again, I can do F times S, and hopefully S times M will be the same. And it is. But again, the reason that that's important today, right? When we say F times S is equal to S times M, you'll notice that your M was a diagonal matrix. Basically what I'm saying is F is diagonalizable. Because what? What could you do with F? You could write S negative 1 times F times S equals that M. Because you just multiply, right? And that was the definition of diagonalizable. And the diagonals, the diagonal matrix you have is actually the matrix of eigenvalues, right? Again, M is the matrix of eigenvalues. And so there's a command in MATLAB called eig, and it spits out the eigenvalues somehow, okay? But a better way to implement this command is the following. You can actually get two outputs. V and E is what I was told to use at one point in my life. So if I say VE is going to be the eigenvalues of F, what this will do is it'll spit out two matrices. V will be full of the eigenvectors, and E will be full of the eigenvalues. But you notice that that V is definitely different than our matrix of eigenvectors we used. Where was it? S? Yeah, there's our matrix of eigenvectors. S. So why do they do theirs? Do you recognize any of those decimals?
Well, the fourth column used to be half of.
Yeah, that's right. So like I can type this. I can type, let's look at matrix V. Let's look at just, I don't care which row, so I'll put colon, comma, 4. That means I don't care which row, but I want column 4. That's the one you're talking about, right? And if I do F times that, Well, you could see it's an eigenvector, right? But why did they choose to use the matrix full of halves instead of the matrix full of ones? And the answer is they wanted a unit eigenvector. What does that mean? It means the length of that vector is 1. How do you find the length of a vector? Do you guys know that?
It's the magnitude, so it'd be all of those squared.
Yeah.
Sum of them.
And when you square a half, what do you get?
A quarter.
So a quarter plus a quarter plus a quarter. Yeah. So that's kind of cool. I mean, I could do this too. I could say, what about f times the third column of v? That should just give you back the third column of v, because we know its eigenvalue is 1. And I could say now, okay, what is the norm, which is a fancy way of saying length, of my answer? And they'll say it's 1. That's how long it is. Okay? So that's kind of cool. Actually, the whole chapter 7 that I mentioned that we could spend time on is all about norms. Norm vector spaces. But we only have so much time. Math majors would benefit from that the most. Still good for you guys to see a little bit of it. So let me show you the last exercise. Since a bunch of people are interested in computers, this is probably worth showing. It says compare the matrices f to the k power s and sm to the k power for various integers k. Then it says which product requires fewer computations. Well, let's do that. So, okay, here's f. Here's f squared. Oh, cool. And here's f squared times, do we really have a k in there somewhere? Oh no, f squared times s. F to the k power times s. That's what we get. Here is, the other thing we're supposed to compare it to is s times m to the k. Again, here's what s was. So that's interesting. And what happens, what is m squared? Do you guys know what happens when you square a diagonal matrix? Well, you just square the entries on the diagonal. That's kind of nice. Diagonal matrices are really nice. And so I guess if I do s times m squared, you get the same thing as if you did f squared times s. So the question is, which one requires fewer computations? S times m squared, right? When you do matrix multiplication, that's a lot of work. Think about just the ones we do in our... remember that one day we had a quiz where I had you guys multiply matrices by hand? They were 2 by 2 and it still took forever. This is a 4 by 4 matrix. Of course, it seems to do it instantly, but it doesn't. You could take large matrices and multiply them, and it takes time, you know. But diagonal matrices, right? You can really get away with doing things quickly. And so it's kind of interesting. Suppose that F is a matrix that you want to... Remember how it represents a linear transformation? Suppose that you want to apply a linear transformation over and over and over again to something. So maybe we want to do f to the, 20th power. Well, again, it did it very quickly. Okay, all right. What if you want to do f to the 200th power? Oh, be careful, Paul. Okay. I'll push it. Ah, too bad. It knew it's in trouble.
What's that mean? Applying the transformation is that infinitely small?
Or infinitely large. Probably infinitely large. That's interesting, actually. What did we just do? We did 200 last. Let's try 500. Too big. 300. Oh, yeah, look. It's 1 times 10 to the 209th times this stuff. Okay, so this is a crazy way to do it, right? The correct way to do it would be what do we say? S times m to the k. So what happens if I do m to the 200th, right? Or 300th? Or 300th? Well, these are basically 0. Why? Because what was m? So why does it think m to the 200th made those zeros? That's a problem. That's a typo.
Is the decimal places so small they only show the 4 0 places?
Look at m to the 20th. It says it's 1 times 10 to the 13th times 0. That's interesting. Here, what's m to the 5th? Okay, well, at least now it knows it's ones. But this thing's getting huge. What happens is, when you do m to a big enough power, that number starts getting really big. And as it gets big enough, eventually it's going to switch to scientific notation. And when it switches to scientific notation,
You're also dividing the ones by the...
it's going to think that the number you care about the most is right down here, because it's the biggest. And so now it just kind of, those have left the realm of significant digits. So you could see where what are called badly scaled matrices, matrices with entries that are very far apart, are very tough to deal with for computers. And that's an issue that makes things like finding eigenvalues difficult sometimes for large matrices in particular. That's kind of cool to see. Yeah, I'm glad we showed you that based on what you're interested in.